Extrusion is the key step in 3D printing of concrete materials. Extrudability is a property that shows how easy it is to extrude the material and push it through the nozzle. We can define extrudability as the ability of the material to flow continuously through a nozzle without any segregation. Also, to form a continuous filament without voids and discontinuity. Let me highlight that the extrudability of a print material not only depends on the material parameters like yield stress, viscosity, aggregate size, fiber content, and so on, but also depends on the printing process parameters like print speed, extrusion rate, or even the geometry and the shape of the nozzle and extruder. So, we need to consider process-induced parameters when evaluating extrudability of a certain mix design. A concrete mixture could be extrudable in a certain extruder, but could get totally blocked in another printer. The extrudability of a concrete materials can be evaluated both qualitatively and quantitatively using different test methods. Quantitative evaluation of extrudability involves measuring the force, torque, or energy that is required to extrude the material and push it through the nozzle. A typical force displacement or torque rotation relationship during extrusion is shown in this graph. Obviously, the mixture that requires less force to be pushed through the nozzle is considered to be more extrudable. The mixture is considered not extrudable if the force required for pushing the material is higher than the extruder capacity. The noise that you may hear in this video shows that we have reached the maximum load capacity of this particular stepper motor. One important lesson that we learned in our experiment is that increasing the extruder load capacity by using a beefier motor is not necessarily the solution. Aggregate or fiber blockage is a common issue if mixture proportion is not well designed. The experiment shown here is a fiber-reinforced concrete mixture in which fiber clumping occurred and blocked the nozzle. In this case, it doesn't matter how much force we apply to this mixture, it is not coming out of the nozzle. In case of blockage, increasing the load capacity is not helpful. In our experiment, an extruder barrel almost exploded when a very high force was applied to the fiber-reinforced concrete mixer to push it out of the nozzle. When aggregate or fiber accumulate near the nozzle and block the outlet, it's almost impossible to push the material through. Even if the material is pushed through the nozzle, it may not be homogeneous. Optimizing a mixture proportion to reduce the risk of blockage and to enable continuous flow through the nozzle is a big topic, and it's beyond the scope of this discussion. I may just highlight the importance of the solid particle optimization and its impact on extrudability. The two mixtures that are compared here have the same amount of cementitious material. Even the water content and sand to body ratio is the same. The main difference between these two mixtures is the aggregate gradation and the packing density. The mixture with the higher packing density showed a much better extrudability in this test. Another important lesson that I should highlight is that evaluating extrudability only based on energy or force tests may not give us a complete picture of the extrusion process. Filament inspection tests, which evaluates the quality of the deposited filament, can provide a better understanding of the process. Qualitative assessment involves examining the ability of the printing material to be continuously extruded and the quality of the extruded filament. Combining the quantitative extrusion energy test with the qualitative filament inspection method is a useful technique for evaluating extrudability. In the filament inspection test, one layer of the filament is printed and examined. The material is considered to be extrudable if the printed filament satisfies the continuity, conformity, and consistency conditions. Filament continuity means successfully extruding the printing materials without any blockage, tearing, and cracks. filament conformity shows how much the deposited filament conforms to the nozzle outlet or the target filament size that was designed previously. Consistency, on the other hand, reflects how the printed filament remained consistent along the filament length. In other words, it shows the variation of the deposited filament. Less variation shows a better extrudability. Another lesson that we learned is the importance of syncing the extrusion rate and the printing speed with the material parameters. To achieve extrudability, the velocity of the print head should be synchronized with the extrusion rate. Otherwise, the extruded layer is likely to become either crumpled or teared or discontinuous. Here is a test that we developed for finding the optimum print speed based on the material properties. In this test, multiple filaments are printed with a constant printer head speed, but at different extrusion rates. Then the filament conformity and consistency are measured to determine the optimum extrusion parameters. In summary, a successful 3D printing requires an extrudable material. The material parameters and the process-induced parameters have a significant effect on extrudability. So optimizing the extrusion process requires a good understanding of the material flow behavior in the extruder and the link between the process-induced parameters and the material properties.